In this video, we'll be creating several transition shaders as well as a scene manager to use them with. If you're new to creating shaders, be sure to watch the video from the start, as I'll be explaining some of the fundamental things that you'll need to know in order to fully understand the diamond sweep shader. If you're already familiar with how shaders work, or you just want to see the implementation, then use the timestamps in the description to jump to whichever you're interested in. To speed things up a bit, I've set up a couple of scenes that will be used to test the transitions, and I've created the folder structure that I'll be using to organise things. Let's start with the horizontal sweep, which will be one of the simpler shaders that we're going to be making. First, let's add a canvas layer and a colour rect object. This will be the object that we animate in and out with the shader, so whatever colour we select for this will be the colour that we transition into. For now, I'll set this as black. Next, we'll create and apply a new shader material to the overlay object. And assign it a new shader, which we will call horizontal sweep. There are several different shader types listed under mode. As we are making a 2D shader, we'll choose the canvas item type. When we open up the shader in the shader editor at the bottom of the screen, the first thing you're going to notice is that the syntax of the template is different to what you may have seen before. Shaders don't use GD script, but instead use a C-like language, similar to OpenGL's shading language. We can see the default template adds in 3 functions, along with descriptions of what each one does. For this video, the only function we'll need is the fragment function, which, as the comment says, will be called for every pixel of the overlay shader material, and will allow us to modify the colour value of each pixel individually. As we are making a simple sweep transition, we won't need to do much manipulation to the underlying colour. We'll simply want to choose to either draw the pixel or discard it, depending on whether that part of the screen should be covered by the overlay. Before we begin to implement the fragment function, it's important to understand the 2 types of coordinates that we have available to us inside the fragment function. We have the coordinate of the pixel in screen space, available via the frag_coord object, and we have the UV coordinate of the pixel, available via the UV object. Before we continue, it's very important to understand the difference between these 2 values. The screen space coordinates are an absolute representation of where the pixel resides on the screen. For a 1080p window, the top left corner of the screen would be 1:1, and the bottom right corner would be 1920/1080. The UV space instead uses floating point numbers ranging from 0 to 1, where the top left corner would be 00, and the bottom right corner would be 11. The size of the UV vector is the same no matter the resolution of the screen, meaning the center point of a 1080p screen and a 4K screen would both be 0.5, which makes it useful for creating shaders that need to support any screen size. Something worth noting as of March 2024 is that the official documentation for the frag_coord variable is currently showing incorrect information. It states that the origin is the lower left corner of the screen, but it's in fact the upper left corner. This should be rectified soon, as a fix has been submitted on GitHub. With that in mind, let's now take a look at implementing the fragment function. Firstly, we need to add 2 variables that we can access from outside the shader, which we can do by using the uniform keyword. The first variable is going to be called progress, and will be a float that ranges from 0 to 1, 0 being the starting point and 1 being complete. The second variable is going to be called fill, and will be a boolean that indicates whether or not we are filling the screen with the underlying colour or not. As the progress variable and the UV coordinates both share the same range of 0 to 1, the code to make our colour sweep from the left of the screen to the right of the screen will be very simple. If we take a look at this illustration, we can see if the progress of the transition was at 0.4, any pixels that have an X value that is less than the progress would need to display the underlying colour, and any that are greater than it would need to have no colour. So first, we'll check if the X value is greater than the current progress. If it is, and we are filling the screen from left to right, we want to discard the pixel so it has no colour and is transparent. We can do this by using the discard keyword. When the fill variable is set to false, we need to do the inverse of this so that any pixel that is further to the left is discarded. So we'll add another block to do just that. Now if we use the progress slider in the shader parameters, we can see that the overlay object will only draw to the area of the screen where the progress variable covers. Next, we'll look at creating a vertical sweep transition. The logic for this will be the same as the previous shader, except we'll be working on the y-axis instead of the x-axis. If a pixel's y-coordinate is less than the current progress value, we'll leave the colour unaltered. Otherwise, we'll discard the pixel and render what is underneath the overlay object. Let's go back to the overlay object's material property and create a new shader. We'll name this one Vertical Sweep. Just like the previous shader, we're only interested in the fragment function, and we'll discard the pixel depending on whether y exceeds the current progress or not. If we now use the progress slider, we can see that it will fill the screen from the top, and if we unset the fill flag, it will instead reveal the underlying screen from the top. The next shader that we're going to make is the horizontal split transition. This is going to be a bit more complicated than the previous two. This shader is going to expand the overlay from the center of the screen outwards. In the horizontal sweep shader that we made to begin with, the value of progress and the value of x both had a range of 0 to 1, making the logic simple. In this case, things are a bit more complicated, as we are no longer going to be starting on the left side of the screen. Instead, we want the origin to be in the center of the x-axis. Likewise, we have the additional complexity of needing to fill the left and the right hand side of the origin point in a symmetrical way. There are two ways we can go about this. One would be to check if the pixel falls in the left or the right hand side of the screen, and then adjust the checks we are making accordingly. Or, what I'd say is the easiest way, we can shift the scale of the x-axis and then work on the absolute values. This might sound a bit complicated, but this illustration should help visualize what we'll be doing. If we shift the x-axis by negative 0.5, it will now range from negative 0.5 to positive 0.5, as opposed to ranging from 0 to 1. In our horizontal sweep shader, a progress value of 40% covered the range of 0 to 0.4. Now that we have shifted the coordinates 50% to the left, however, 40% would cover the range of negative 0.2 to positive 0.2. By shifting the x-axis like this, the negative space represents the left half of the screen, and the positive space represents the right half of the screen. So, let's start implementing the fragment function. We'll start by creating a new shader, and using our horizontal sweep shader as a basis for this one. The first change we'll make is to subtract 0.5 from the x-coordinate. If we now use the progress slider, we'll see a progress of 0% discards the pixels on the right side, but not on the left side. This is because the left half is now in negative space, and our code is only checking the positive space. As we want our animation to be symmetrical, we can use the abs function to get the absolute value of x, allowing us to treat both negative and positive numbers the same. If you haven't used the abs function before, it simply removes any sign from a number. So abs 0.2 would return 0.2, and abs negative 0.2 would also return 0.2. If we now test the slider again, we can see a value of 0 discards the pixels on both sides of the screen, and now fills the left and the right sides accordingly. There is still one more change we need to make, however. When the progress reaches a value of 0.5, the entire overlay is shown, as opposed to half of it. This is because we offset the x-axis by 50% into negative space. To fix this, we simply need to normalize it back to the same 0 to 1 scale by multiplying it by 2. And now the shader works as intended. The last transition type that we're going to discuss is one of my favourites, and is also the most complicated of the four. This is going to build on top of what we've gone over so far in the previous shaders. It will look as if it's sweeping across the screen from left to right, like our horizontal sweep did, but by creating diamonds that get bigger as the progress increases. First, let's take a look at forming a single diamond in the shader to get an understanding of how we can form the required shape. As can be seen in this illustration, it's possible to form a diamond by mirroring one right angle triangle across all four quadrants. If we can figure out how to create a right angle triangle, then we can use the same axis shifting method that we used in the horizontal split shader to mirror it into each quadrant. When we were animating only across the horizontal or vertical plane, it was as simple as checking if the x or y coordinate was less than or more than a specific value. When working across a diagonal plane, it's a bit different in that we need to check the sum of the coordinates. If we look at this illustration of a right-angled triangle in UV space, we can see that the sum of the points plotted along the hypotenuse of the triangle all sum up to 1. Likewise, if we look at the yellow points plotted in the centre, each sums up to 0.5, no matter where they are on the line. By doing this sum, it's possible to make a comparison with the progress value and determine if the pixels should be drawn in the same way that we have done with our other shaders. If we implement this logic in the fragment function, and then use the progress slider, we can see that it works as intended. So next, let's mirror this across all 4 quadrants to form a diamond. We can do this using the same method that we used in the horizontal split shader by shifting the coordinates by -0.5, but this time we'll shift on both the x and the y axis. And once again, if we use the progress slider, we can see that it will animate as intended. As we want to fill the screen with diamonds, as opposed to having just one single diamond, we'll instead be using the screen space coordinates as opposed to the UV coordinates. To achieve this, we're going to need to add a new variable to define how big we want our diamond to be in pixels, which will default to 40. Next, we're going to calculate the x and y values that we'll be using instead of the UV values. To do this, we're going to need to split the screen up into a grid by using the screen space coordinates stored in fragcoord. We'll do this by dividing the screen space coordinates by the value of size and take the fraction of the result. This will give us a value that is normalized in the same way the UV coordinates are. As an example of how this works, if we were processing pixel 39 on the x-axis, we would divide 39 by 40 and the result would be 0.975. Likewise, if we were processing pixel 79 on the x-axis, we would divide 79 by 40 and the result would be 1.975. By taking the fraction of the result, we'll always have a normalized value between 0 and 1 that we can use in each section of the grid, the same way we would use the UV coordinates for the entire screen. Lastly, we'll subtract 0.5 to shift the values in the same way that we did in the horizontal split shader. If we now test with the progress slider again, we can see the screen is split into a grid of diamonds that will animate in and out. We now have one last thing to add, and that's the sweeping motion. To do this, all we need to do is add the UV coordinate to the comparison. And as the UV coordinate has a maximum value of 1, we'll need to scale progress by 2, as the max value of x, y, and uv.x is 2. With this change added, the diamonds will now sweep across the screen on the x-axis. If you wanted to make this work diagonally, you could also add uv.y and raise the scaling of progress to 3. I personally prefer horizontal animations though, as they look a lot more uniform on 16:9 screens. Now that we have our shaders, it's time to piece it all together by finishing creating the scene manager. We'll keep the loading screen simple by having a label that will pulse while the next scene loads. First, let's add a margin container to our scene, and add a label as a child of the container. I've already added a font to this project, so I'll assign that to the label in the label settings property, and set the font size to 64 pixels, as well as enabling the uppercase option to make the text look a bit more uniform. In the margin container properties, we'll set the anchor point to be the bottom right corner of the screen, and set the margins on each side to 20 pixels in the theme overrides section. Lastly, we'll center the pivot offset property by dividing the size by 2. We need to do this so that when we create the animation to make the label pulse, it will do so from the center rather than the top left, like this. Next, we're going to create the transition animations. Add an animation player to the scene. Now create a new animation named In. We'll set the length of this animation to 0.7 seconds. We'll set up the progress property of the shader material to animate from 0 to 1 over 0.5 seconds. If we play that back, we can see the shader animating nicely. We'll also make sure the fill property is always set to true at the start of the animation. Now, we'll set up the initial animation of the loading label. We'll set the initial scale of the margin container to 0, as we are going to want to scale it from 0 to 1 once the overlay has filled the screen. We'll want the growing effect to start at 0.5 seconds, so we'll move the final value to 0.7 seconds, and make sure that we have two keyframes set to 0 at 0 seconds and 0.5 seconds. If we play the animation back, we can see it's working fine now. It's very unlikely that the label will be visible at such a small scale, but to be sure, we'll add a track for the label's visible property, and we'll make sure it only becomes visible at the point that we're starting to scale it from 0 to 1. Now, we'll create a new animation called Pulse Text, and animate the scale of the margin container between 1 and 0.8 over 1 second. If we play that back, it looks good. We'll also set it to loop by pressing this button. Lastly, we'll create the animation to transition out, which will be called out. This will be similar to our in animation. The progress will animate from 0 to 1, but we'll set the fill parameter to false this time at the start of the animation. As we'll be going from the pulse animation to the out animation, we can't be sure what the scale of the margin container will be when the out animation starts, so we'll be scaling the container down in code rather than inside the animation player. It is worth noting that the capture update mode does provide this exact functionality in the animation player, but it's currently broken in the Godot 4 branch. This should be fixed in the future though. So now, let's start coding up the script for the scene manager. First, we'll need to add two signals that will be used to indicate when we have transitioned in and out of the loading screen, which we will call transitioned in and transitioned out. Next, we'll set up references to the animation player and the margin container. And add two functions that will handle the animations for us. The first will simply play the in animation that we created earlier. The second will play the out animation and also tween the scale of the margin container. Now, we'll create the function that will be called from our scenes when we want to transition to a new scene. We'll first call transition in to animate the overlay onto the screen and wait for the transitioned in signal to be emitted. Once it is emitted, the overlay will be visible, so we can now load our new scene and remove the previous one. To do this, we'll get the root node of the scene and remove the last child node by calling free. And then add our newly loaded scene in its place. The reason we do it like this is because the scene manager will be automatically loaded into the scene tree as the first node, and the scene we are launching will be the last. We'll set this up now. Go to Project Settings and to the Auto Load tab, and then navigate to the Scene Manager scene and add it as a new node. Now that we've added the Scene Manager as an auto load node, let's launch the project and take a look at the remote scene tree to help visualize what's happening a bit better. As you can see, the Scene Manager node is the first child, and our scene that we have launched is the last node in the tree. Back in our script, let's continue to implement the transition to function. Once the new scene is added to the tree, we're going to call a function that we'll create later called load scene and wait for the loaded signal to be emitted from the scene. This will allow us to do any caching or any other heavy lifting before we transition into it. Once the new scene has finished loading, we'll call another function that we'll create later called activate. The activate function will execute any logic that will be required as the new scene becomes active, like beginning pathfinding or playing background music. Now, we're going to need to connect the animation finish signal of the animation player to our script. In here, we're going to check if the name of the animation that has just finished is in. If it is, we'll start playing the pulse text animation and emit the transitioned in signal, which the transition to function waits on before starting to load the new scene. If the animation that has just finished was out, then we'll instead emit the transitioned out signal to flag that we need to activate the new scene. That's all we need to do with this script for now. Before we move on to implementing the script to use as a base for all of our scenes that can be used with the Scene Manager, I'm going to create a new action in the input map to use for demonstration purposes. Now that we have the action set up, let's open up scene 1. And in here, we're going to create a new script, which we will call scene.gd. The first thing we'll do is add the loaded signal, which the Scene Manager waits on before transitioning out. And we'll add an exported variable, which will allow us to specify the path of the next scene in the editor. We'll check to see if the action we just created is pressed in the process function, and if it is, we'll call the transition to function with the path specified in the next scene variable. Lastly, we need to add the other functions that the Scene Manager assumes will be present. The first of those is activate, which we'll leave empty, as we have nothing that we want to do when the scene becomes active. And the second is the load scene function. In here, we're going to create a timer to simulate some wait time for demonstration purposes. We'll make the function wait for 3 seconds before we emit the loaded signal. Now we'll choose the path to scene 2 as our next scene to finish up scene 1. Next, we'll open up scene 2 and assign the same script to the root node, but this time we'll choose the path to scene 1 as the next scene, which will allow us to loop between the two scenes by pressing the escape key. Lastly, we're going to go back into the Scene Manager script and add a bit of code to the transition to function that we missed earlier. Once the new scene is finished loading, we'll want to call the transition out function to begin animating the overlay back out and wait for the transitioned out signal to be emitted before activating the new scene. And now, if we run the project, we can hit escape and transition to the next scene with our transition shaders animating in and out of the loading screen seamlessly. Although we have used a color rect as our overlay, it should be noted that the shaders will work on any canvas item, so you could apply them to a sprite and have a background image animate in rather than a plain colour as we have done here. One last thing worth noting is that if the label appears in the corner when you initially launch the scene, you should take a look at your reset animation and make sure the scale is set to 0 or the label visibility is set to false. The reset animation will be executed when you launch a scene, so depending what order you added your initial keyframes will determine what value is in the reset animation. You can edit this animation like any other though, if you have accidentally added the wrong ones. If you want to learn more about the Godot shading language, I'll leave a link to the documentation in the description. Let me know in the comments if you found this useful, and if you have any questions, let me know and I'll try to answer them.